In our last example for section 5.1, we are told to use the substitution x equals 2 times the tangent of theta, where theta is an angle between 0 and pi over 2, or 0 and 90 degrees. So the angle we're technically dealing with is in this first quadrant. To write that expression, the square root of 4 plus x squared, as a trig function of theta, some function of theta has to be used to represent this exact quantity. Now, does this exactly make sense? What if we rewrite it a little differently to see exactly what it's asking us to do? The way that I would phrase this sentence is by saying the following: that we need to rewrite the square root of 4 plus x squared as a function of theta using the substitution x equals 2 tangent theta, so long as theta is between 0 and pi over 2. Okay, so using this information, we can also see a little bit more directly what the instructions are asking us to do. We need to rewrite an entire expression using the substitution that we've been given. Now, the expression we're dealing with is the square root of 4 plus x squared. But in this particular case, x is equal to 2 tangent theta, so we can just substitute that in and see what's going to happen. That's going to give us 4 plus 4 tangent squared theta. So we can actually factor out the 4 from each of the individual terms under the square root symbol. So that's going to give us the square root of 4 times 1 plus tangent squared theta. The whole thing is still under the square root symbol. Now, 1 plus tangent squared theta is actually one of those Pythagorean identities, the one that we don't see as often, but this is equal to secant squared theta. This is another Pythagorean identity. We can just write that down on the side here, where 1 plus tangent squared theta is exactly equal to secant squared theta. So we're using this to rewrite our expression. Now that we have rewritten it that way, our expression becomes the square root of 4 secant squared theta. So 4 is a perfect square. We can bring that out of the square root as a 2. But so we can bring out the secant squared as well, because there's 2 secants in them multiplied together. So this also comes out, and we end up with 2 secant theta. And that's actually our answer. What we're basically saying here is that this expression, the square root of 4 plus x squared, can be rewritten using this trig function here, where the secant of theta is a positive value for the angle theta that's anywhere between 0 and pi over 2. Meaning, if we have the first quadrant taken into consideration with an angle theta in here somewhere, the secant is going to be positive because in the first quadrant, cosine is positive. So is sine and so is tangent. But in the first quadrant, if cosine is positive, then the secant is positive as well, which means this works. Now, one of the ways we can actually relate the original question here with the expression that we were able to calculate is by actually referring back to the substitution that we were told to do. So x equals 2 tangent theta is actually going to be really useful for us to kind of relate the x and the theta to each other. So we're just going to take that substitution equation, x equals 2 tangent theta. And if I solved this for tangent theta as its own thing, so I'm just going to solve for that on its own, I'd have to divide my equation by 2 on both sides. So x over 2 is equal to tangent theta. Now, if we were dealing with a right triangle, where this right triangle would have to sit in the first quadrant, given the information we had originally from the value of the angle theta being between 0 and pi over 2, that means that in the first quadrant, we technically have a triangle like this, where the angle theta is that one down there, the central angle of the triangle. And if the tangent of theta is given as x over 2, x is the opposite and 2 is the adjacent. So in this situation, we're going to write this down as x over 2. And when we look at the triangle that we now have, this missing side can be found by taking x squared and adding it to 2 squared, and that's going to be the hypotenuse squared. So we're using the Pythagorean theorem to figure out what's the actual magnitude or the size of the hypotenuse. What's the value there? So we're just going to solve for h, and h squared is going to be equal to x squared plus 4, which means h is equal to the square root of x squared plus 4, which if we look back at the original problem, that was exactly what we were told to evaluate and bring in some theta to figure out a new expression for it. So going back to the triangle here, this is exactly the same thing as the square root of 4 plus x squared. So the value of the hypotenuse here is the square root of 4 plus x squared. And we're trying to see if 2 times the secant theta is actually equal to the square root of 4 plus x squared. Now, we used algebra and we plugged in a whole bunch of trig substitution to get it to equal 2 times the secant of theta. But using the triangle here, we can also say that the secant of theta from the triangle is equal to 1 over the cosine of theta. And if cosine is the adjacent over the hypotenuse, then the secant is going to be the hypotenuse over the adjacent. So secant of theta here is going to be the square root of 4 plus x squared over 2, because we're doing hypotenuse over the adjacent for secant theta, which means if I multiplied both sides of my equation here by 2, then the expression that I was originally dealing with is, in fact, equal to what we determined that it would be equal to. So our solution checks out.